the DC transfer characteristics of an inverter. So inverter is a basic CMOS circuit. It is formed of combining one NMOS and PMOS. Yesterday we were discussing that in order to match the conductivity of both NMOS and PMOS, we have to choose the size of PMOS twicer than that of the NMOS. So this is the structure of normal standard CMOS inverter. So drain and drain connected together, we are taking output. Gate and gate connected together, we are giving the control input. Actual inputs are VDD and ground. Both are connected to source of PMOS and NMOS respectively. The working of an inverter is when I am supplying a zero voltage. As you know, when we are supplying zero, your PMOS will be switched on and the NMOS will be switched off. Actually, your PMOS is getting into saturation region, NMOS will be in cutoff region. And when PMOS switched on, the output will be directly connected to VDD, so you will get 5 volt at the output. That is logic 1. So when we are applying 5 volt, that is logic 1 as input, PMOS will be in cutoff region and NMOS will be in saturation region. So output will be connected to ground, so we will get 0 volt or logic 0 at the output. So in the DC transfer characteristics, we will be discussing about we will be considering both the working of NMOS and PMOS combinedly, and we will be discussing the operating regions and what is happening at each and every operating point. So if you see the characteristics curve of a CMOS circuit, so here we have combined both NMOS and PMOS characteristics, IV characteristics curve. The first quadrant refers the characteristics of NMOS. The third quadrant shows the characteristics of PMOS. So in order to understand the DC transfer characteristics of an inverter, we will be initially shifting the characteristics of PMOS also to the first quadrant. So your characteristics curve look like this, and the overlapping points will be marked as operating points. So you will be having 5 different operating points. These are all the overlapped points. The initial point is this one, and the final point is this one. So your characteristics curve look like this. You will be having 5 different operating regions. The first region is between. Actually, this is the curve drawn between input voltage and output voltage. So initial operating region is between 0 and threshold voltage. The second region is between threshold voltage and VDD, half of the supply voltage. Operating point C at VDD by 2, and fourth one is D, and fifth one is C. So here we will be discussing what are all the input voltage conditions and output voltage conditions at each and every operating point. And particular operating point, what is the status of PMOS and NMOS, whether it will be in saturation region or cutoff region or linear region, those will be discussed. If you see this table, by comparing this only we are doing. We are going to compare the operating points as well as the table now. The first region is between the input voltage between 0 and VTN. At that time, your PMOS will be in linear region and the NMOS will be in cutoff region. Actually, we are applying a logic 0 at the input of CMOS inverter. When we are applying logic 0, your PMOS will be in on condition. Slightly, it is getting into on condition, and NMOS will be in cutoff region. So at that time, output will be connected to VDD through the source of PMOS. We will be getting maximum output. That is they have mentioned here. The region B is between VTN as well as VDD. We are increasing the voltage above threshold voltage. If we are using germanium transistor, um, this VTN value will be around the zero point 0.3, and if we are using silicon, it will be around 0.7. From 0, we are increasing the voltage above the threshold voltage. As we have discussed yesterday, when we are crossing the threshold voltage, NMOS will be scattered on. So at that time, NMOS will be in linear region, sorry, saturation region. PMOS device will be in linear region. So at that time, output will be less than VDD or greater than VDD by 2. The region C. At this particular point, your both NMOS and PMOS will be in saturation region. So at that time, we will be experiencing a short circuit between VDD and ground when both NMOS and PMOS will be in on condition. Uh, your circuit will be connected directly to the ground. At that time, high IDD current will be flowing from VDD to ground, a short circuit. Okay. The fourth region is D. So this is the voltage conditions between VDD by 2 and VDD minus VDD. At that time, your PMOS will be in saturation region and NMOS will be in linear region. At that time, output voltage will be less than VDD by 2. The last region is E. At that point, my input will be having the maximum value, that is 5 volt or VDD. So in this time, PMOS will be in cutoff region and NMOS will be in linear region. So when your NMOS is in on condition, your output will be directly connected to the ground. So zero voltage will be at output for logic 0. So this is the explanation about DC transfer characteristics of CMOS inverter. In that, we have an important derivation that how this V in as well as V out are VDD by 2 in both the cases. If you see this curve at point C, your output as well as input are having the same value. You will be having a derivation. In your third edition book, it is not there, but in this PDF, they have clearly mentioned we have also derived that in class. So before getting to that, we need to know what is the beta ratio effect. So actually, beta ratio effect describes how the characteristics curve shift is happening in the real time or in the practical cases. In that, we will be discussing about three cases: low skew circuit, high skew circuit, and unskew circuit. So the beta P and beta N value is like this. Yesterday we have seen this formula. Beta P is mu C naught x W by L. That is the beta value. This is the constant we have referred as beta. Actually, beta P is mu C naught x WP by WL. Because why I have mentioned the WP, WN, LP, LN. Um, the NMOS and PMOS will be having different size. Yesterday we have discussed also we will be choosing the size of PMOS is twicer than NMOS, and most of the cases length won't be changed. Length most will be mostly the same, but width may not be the same. Uh, Beta P mu C naught x value will be the same with respect to the manufacturer. So mu C naught x WP by WL is beta P. So mu in P naught x WN by WL is the beta N. So if you consider beta P by beta N ratio, so we will be getting a ratio of WP by WN into LN by LP. So mostly this value will be constant for equal for both NMOS and PMOS. Only the width will be varying. So mainly beta P by beta N ratio depends on the width of both the transistors. So initial case beta P equal to beta N. At that time beta P by beta N ratio will be equal to 1. That type of circuits are known as unskewed circuits. Mostly the unskewed circuits are used for all the designs, but in some applications depending on the need we will be moving on to high skew or low skew circuits also. So high skew uh, here they have mentioning as beta P by beta N ratio, they have equated to a constant called R, called beta ratio. So if this beta P by beta N ratio is greater than 1, that type of circuits are known as high skewed inverters. If beta P by beta N ratio less than 1 means that type of circuits are low skewed circuits. If you compare this, if beta P by beta N ratio is greater than 1 means WP value will be high. So width of the PMOS will be very high. So if low skew means beta P by beta N ratio less than 1, at that time WN value will be high. So we can compare the graph. So this is the transfer characteristics drawn for different beta ratios. Uh, Beta P by beta N equal to 1. This is the actual graph what we have seen earlier. uh, by considering unskewed circuit. If beta P by beta, if beta ratio increases as PMOS size increases, uh, the characteristics curve shifted right towards right. And if you are moving towards a low skew, the characteristics curve will shift leftwards. So depending on the need in different applications, we will be considering different beta ratio inverters. So this is the explanation, the derivation for how that input and output value, input voltage and output voltage equal to VDD by 2 that we have seen in that characteristics curve. For that derivation only we are going to see now. By equating the current flowing through NMOS and PMOS in saturation. So if you consider here, so this is the output current flowing in NMOS in saturation region. Why? Because I am discussing about saturation region. In this particular point, both PMOS and NMOS are in saturation region. That's why we are equating the current in saturation region. So beta n by 2 into V in by Vtn the whole square. Here actually VGT only they have mentioned here. Uh, the drain to source current in PMOS, that is beta P by 2 equal to V in minus. Here we need only threshold voltage to make the NMOS in saturation region. But here we have to overcome the VDD voltage which is connected to source. That's why VDD plus VTP coming here. Minus of VDD plus VTP. So expanding that minus, we will be getting minus VDD minus VTP. That's why we have to consider VDD here. So beta P by beta P by 2 into V in minus VDD minus VTP the whole square. So by equating and we are rearranging the equation to calculate V, we will be getting the formula like this. So in this this R refers that beta P by beta N ratio. So here we are going to consider the unskewed inverter. For unskewed inverter, this R value equal to 1. So the denominator will become 2. The numerator will become VDD plus VTP plus VTM. So this will become 1. So here, if you compare the threshold voltage of both NMOS and PMOS, both are having opposite values. For example, VTN equal to minus of VTP. So this may cancel each other. So we will be getting Vin equal to VDD by 2. So that is the explanation why we are theoretical explanation about input voltage, output voltage equal to VDD by 2 in the operating point C. At that time, both NMOS and PMOS will be in saturation. Next one is noise margin. This is also a subtopic in DC transfer characteristics. Why we are analyzing noise margin is in practical cases, ideal cases, we didn't discuss about any external noises. Many external noises will be available in your system. Here we will be analyzing how an external noise can affect the circuit, or how much noise can be if you are considering noise in your system, how much allowable noise which cannot alter the output characteristics. That only we will be analyzing here. So for that, what we are doing for this analysis, we will be manually adding noise to the circuit, and we will be checking the output. So how much noise can be adapted so that there won't be any change in the output. So that only noise margin refers. Noise margin is the maximum allowable noise on the input so that the output will not be corrupted. That is the case of noise margin. So noise margin has two parameters, high noise margin as well as low noise margin. So that calculation only they have shown here. For that, they will be connecting cascading two inverters, and we will be observing the output characteristics of the first inverter and the input characteristics of the second. So this is the noise margin what they have referred. For calculating low noise margin, they will be considering the low input voltage of the receiver and the low output voltage of the sender. So the first inverter will be acting as the sender, and the second one will be the receiver. So in order to calculate low noise margin, we will be considering low input voltage to the receiver and minus low voltage to the from the sender. For calculating high noise margin, we will be considering high output voltage of the sender minus high input voltage to the receiver. This is the equations for calculating low noise margin as well as high noise.